Welcome to this presentation that's going to discuss the usage of the Imperas tools for RISC-V custom instruction development for debugging within our environment and enhancing the capabilities in True Silicon. A little bit of background on the company, first of all, regarding Imperas and what our focus is. And we believe that nobody should develop an embedded software without simulation. In the same way as you would never consider designing a chip without simulation, we think the same is true here for designing software as well. And our background is that we have engineers who have been involved in EDA for a long time, including technologies such as RTL simulators, ISS, processor development, and synthesis tools. And if you look at the capabilities that we have within our technology, we have a huge library of components from all the major vendors, including ARM, MIPS, Synopsys, and of course, what we're talking about today, RISC-V. And although RISC-V is an ISA, there are many implementations of these, including some of the ones listed here, such as Andes, Sci-Fi, Microsemi, etc. And in terms of our technology, what we do is we provide both an envelope model, which covers all of the aspects of the specifications, but in addition, we provide models of the cores themselves so that these can be run inside of our heterogeneous or homogeneous environment. So now if we look at processor hardware options for accelerating software, there's probably three approaches. You can have an external accelerator which performs some activity based upon the programming from the host CPU. You could have specific extensions to that processor, and some of the things you could think about would be vector extensions or bit manipulation extensions. And the applicability of these would really depend upon the application that you intend to run on this particular device that you're implementing. And then finally, we also have the processor custom extension example as well, whereby you create specific extensions for the application that you're attempting to optimize. And this is really what we're going to concentrate on today. Looking at the kind of activities that you need to go through, the first activity is architectural analysis. And this is especially true for when you're trying to come up with custom instructions. But this information that you get back from the system can guide you to say, okay, do we need to move to a multi-core? Do you optimize the pipeline, improve memory usage and latency? Or indeed, as what we're talking about here, which is to implement custom instructions for your particular application domain. And this is something that's pretty unique to RISC-V, but not, I wouldn't say totally unique. There have been previous technologies that have tried to address this, but I don't think they've addressed it in quite a comprehensive manner in terms of putting in the hooks into the software tool chains as well, such as whether you're using either a GCC-based tool chain or a Clang type tool chain. And the flow you would typically go through here is the first thing is you would characterize your C application. So if we presume that we start with application code that doesn't have custom instructions, then you'll go through the flow of instruction accurate simulation, performing trace and debug to get your application functionally correct, and then to do some kind of timing simulation. And we have these capabilities to put timing annotation back into the environment. This then gives you some function profiling information that you can then use to guide the creation of potential new custom instructions, which would be applicable to whatever your application is doing. And the requirement there is to design the instructions to fit within the custom extension part of the ISA, add them to your application, add them to your model, add potential timing as well, and then you can sort of go back around the loop for doing the characterization of those instructions inside of your application. And so this is where, the main part of where you would do co-optimization of both your application and the instructions that you're trying to use to improve the throughput in your application. And then, of course, once you've got to a point where you're happy with the performance, then the technology will give you additional capabilities to do things such as instruction coverage, line coverage, the performance, automatically generating documentation. And then as the final part of the path here is to get the full stack up and running, making sure that you've got compliance tests that run as part of this, and also getting your OSs or RTOSs to run at this point. So what I'm going to do now is I'm going to switch over to my colleague Duncan, and Duncan is going to give us a walkthrough demonstration showing how we can use these approaches that we've discussed here within the technology that we provide, and show how you can start to hone in your application and your custom instructions within your entire application framework to guide this tool set so that you get an optimized instruction set architecture extension for your custom instructions. So over to Duncan.
Hello and welcome. I'm going to show you this example. I'm going to start off by looking at the characterization of the C applications using the Imperas simulation environment and tools. So within our C application we can trace and debug, we can add timing to the simulation, and we can do function profiling and timing information. So I'm going to run the first section, which I'm just going to run instruction accurate simulation of a C application that I'm interested in getting information and eventually going to add custom instructions to. So a C application, it reads some data from a data file, and line by line we process the line. We're actually implementing a char-char-20 style of algorithm, so we have some processing elements on the word of data, and you can see that these 4 functions all equate to the same bit manipulation and rotation, with a different value of rotation being used each time. So let's run our simulation. So simulation is using semi-hosting here, so the algorithm can read information from the host system. So this gives us access to the host standard in, standard out, the file system, etc. So we've got the result of our algorithm execution. We can see we've run just under 2 billion instructions, and the simulation time was around about just under 20 seconds of time. So this is a instruction accurate simulation. This is the expected time using the MIPS rating we've defined for this processor. Now we want to look at adding some timing information and the cycle approximation that allows us to achieve. So I've run exactly the same simulation. You can see here now though we've enabled our cycle timing estimation, and the overall time now is, if you remember, it was previously just under 20 seconds, now 25 seconds. So we're actually giving a more realistic impression of how long the application will take to execute. And now we want to look at where we're spending our time. So we enable the tool, the function profiling tool, on our application execution. So now with the function profiling complete, you notice we've created a profile information graph. So here we can see the functions that are being executed. We've got our 4 functions, which are the algorithm. These are all being called from the process line function, and in turn the 4 functions are calling into our algorithm. And you can see here we're spending 30% of the time of this application execution on this data set is spent in the one function of processing the core of the algorithm. So now we've profiled our application, we want to start adding custom instructions. So now let's look at designing the instructions, adding these into the application, loading the new custom instructions to the model, and also adding the timing information for our custom instructions. So first of all, let's look at the change we make to our application. So you can see here we've got the same core algorithm. We're still processing a line of data at a time, but now our process line function is actually using some embedded assembler that defines our new instructions, the decodes for our new instructions. If we execute that on the instruction accurate simulator, we can see immediately we take an illegal exception. So I've only executed just over 1,000 instructions. The simulator has identified that we're attempting to execute a custom 1 decode space instruction. This is causing an illegal instruction because we haven't got the extension enabled in the model. So the next thing to do obviously is to create our custom instruction. The custom instruction is created using the standard via my APIs. We create decodes for the instruction. So this is the definition of the bit patterns for each of the 4 instructions that we're creating. And we create the behavior of the instruction. So here we're creating or telling the simulator what function provides the behavior. And you can see here we're using the same function, and again we're passing the different rotation value. So our implementation can be either a C function and reusing our previous C algorithm, or the implementation I'm going to do here is to implement fully with the MorphTime API. So you can see that we create the XOR and the rotation by reading the values from registers and immediate value from the instruction. So now with our additional library loaded, we can run our simulation. So here you can see we've loaded our custom library. We have the same result of execution, but now the simulation time is reduced from 20 seconds down to just under 7 seconds. And again, we can run the same profiling and cycle approximate simulations that we did on the C application. In terms of the timing information, then we have a basic definition that we've created here for providing timing information. And in it we add the definition of our instructions. You can see that we've put them all into the same group. And then for this group, we're defining that the instructions will actually take 2 cycles. So there's a cycle penalty for using these custom instructions. With that timing model loaded, we can again run the simulation. And now we see the simulation time has extended to just over 9 seconds. So our timing information has been used to determine a more cycle approximate definition of how long that will take to run. But also this can be used in our profiling. So again, we're going to run the standard same profiling tool, but now on the application using the custom instructions and with a processor model that includes the custom instructions. So again, we've generated the profiling information, and now you can see that the process lines, the whole of the processing of a line, now falls down to just 14%. So if you remember previously, we had the process line plus the functions to implement the algorithm were occupying well over 50-60% of overall time. So we've shown the development of a custom instruction applied to the custom instruction space of the RISC-V processor model. What I'm going to show briefly now is that we can use all the same usual tools with our custom instructions. So we can do tracing, we can do debugging. We saw that we could do the same profiling of the application. So let's start out just by enabling tracing. So this is sort of giving us low-level information of the execution. We've got tracing enabled just for a small portion of the time of the execution. So from instruction 1330 for about 20 or 30 instructions. But we can see here that we have our function process line. Then within the function process line, we're calling the custom instructions. And where the custom instruction is modifying the register, we can see that we're showing the changes to that register. Let's now bring our application up into our debugger. So I'm going to start off by manually putting a breakpoint on main of my function and then executing to that point. So you can see we have full source debug. We have visibility of all of our registers within the core of the processor. And we also have additional information about the processor itself, of where we are. All of the supervisor and system registers are available to us to read, and we can see how many instructions we've executed. We set a breakpoint, run to that breakpoint, and then I can step into my function that's going to call my custom instructions. So I'm just going to turn off GDB mode, because what I want to do is ensure that when I open my disassembly window, the decodes for the custom instructions is coming from the model and not from the using GDB mode. So we'll turn GDB mode back on now, and now we're in instruction mode. Let's step through our code, and you can see we can step into our instructions. As we execute the instruction modify A0, we see the register being modified, and we have the source line debug. So with our custom instructions, we've got the full source line debug capabilities available to us automatically in our development environment. So in these initial stages, we've looked at the characterization of applications, the development of custom instructions, and using those custom instructions. What we also are going to talk about briefly is actually doing some analysis of the instruction. So this is for the developer of the instructions to find out whether we've done fully tested the instructions, how well we've done that testing, and also how well we've implemented the behavior of the instruction. And we'll look also that we can automatically generate documentation which includes the information about our custom instruction work. So first of all, I'm going to look at the coverage information. So we're running this loading a tool. This is monitoring all of the instruction execution while we run our test application. And the report at the end we obtain shows us how much of the execution is spent for each of the different instructions. But more importantly, it's showing us also instructions that have never been executed. So these are obviously instructions that, if this was part of our custom group, would be instructions that we needed to improve our testing. We can also look at the profiling of the instructions. And just to give you an example, I'm actually going to run the profiles using two different implementations of the same instruction. So behaviorally, we have exactly the same result, but we've implemented them differently. One's using the C call, which we're running now. And if we look at the custom instructions, as they're appearing in our log, you can see they're quite high up. The per instruction time spent is quite high, so 15 picoseconds, 11 picoseconds. And so we may want to look at re-implementing, and we can do that using the morph time, which we did, and this is the other implementation. So here we can see we're looking again at the same profiling information, but now our custom instructions, the time spent in them is drastically reduced. So we've got a much more efficient implementation. As I said, we also want to be able to generate documentation. So we automatically generate documentation for all processor models. When we have in custom instructions, we can include these as part of the documentation. So here I'm generating the document for the current processor I'm using, which is the RV32IM. But now, as well as the standard information that's provided for the model, we also get an additional chapter on our extension instructions. So this is all generated information from our custom instruction intercept library, extension library. It gives us the details of the instructions down to the opcode and bit fields. So I've automatically generated this PDF. And then finally, for the developer, is again looking at the testing and looking at how well they have tested all of the different instructions and the different code within the extension library. So we're going to recompile my model for code coverage, and then we'll run the same tests on our model and generate a coverage report. So if I open the coverage report now, you can see we have all the source files that make up the model that we're using, and we also have our custom instruction library. If we go into our custom instruction library, you can see that some lines have been executed, and these are colored green. So these have all been executed, and it tells us how many times these lines have executed. We also have some portions of our code that's colored red, so it's never executed. So basically, this bit of code here is the disassembly output. So this is for tracing, and we haven't run tracing while we've been running the tests in coverage mode. So you can see that we're indicating we've never executed this code. Obviously, this is a small example with 4 instructions implemented. If we had a more complex, then this would very quickly and very easily show us any holes in our testing. So thank you for watching the example. This is available to download and run yourself, and I'll now hand you back.
Thanks, Duncan. So let's now continue on with what we were discussing as part of how to implement these instructions inside of your entire fabric. In terms of the first stage, which is the adding in those instructions, then we've got the further development, debug, and test of the actual software. And we should probably at this point just talk about some of the users of our technology. And one of them is a company called Nagra. And Nagra design chips which work in the video streaming market, whereby they have content security. And one of the big selling points of our technology for them was that they were able to do the majority of the modeling themselves using our capabilities. It meant that they didn't have to disclose what was highly confidential architectural aspects about their design. They could do this themselves. And they are now also doing applications using our technology, heterogeneous and homogeneous, and using all these capabilities that we've discussed. And I mentioned earlier about the library of processors that we have, and we should probably also mention in more detail the RISC-V versions of these. And so we've got all the variants of the Andes cores, the Sci5 cores, and also some of the open source cores, including the open hardware CV32E40P. Which is based upon the original RISC-V core, and we also have things like the low RISC from IBEX as well. And within our technology, as was shown in the previous demonstration, it's we have the capabilities to add these custom instructions into these models in terms of being able to append them into the custom instruction set. In addition to modeling the cores themselves, we also provide platform kits, and what a platform kit does is that, or an extendable platform kit, we should say, is this gives you a basic starting block for your design, including the processor, the basic peripherals, as we see here. So we've got an N25 with a click, timer, and UART, things like this, and you can pretty quickly get applications up and running on this, or even more complex ones such as the Sci5 U540, which is a quad-core processor booting Linux. In fact, it's got 5 cores, but only 4 are visible to the Linux once the Linux is up and running. One of the cores is used during the boot. But building an executable model of the platform itself is only half the story, because what you really need are the tools that sit around this. And this is what we show here, is that you have your core execution engine, but then what you really need is you need the tools, the debuggers that sit on top of this and are able to make use of the data that platform is actually generating by being able to debug, analyze, capture information, and drive the platform in the way in which you want to do within your use models. And these could be interactive use models, or we also have customers that use a lot of this as part of their farm-based infrastructure for huge amounts of regression testing. And so if we talk about verification as part of this as well, so verification is a bit of an overused term for myself, and in particular in the RISC-V parlance, we talk about compliance and we talk about design verification without really being able to pull the two apart effectively, and I'll come back to that a little bit. But again, one of our active customers who are using our technology as part of their reference methodology is a company called Mellanox, and Mellanox actually use our technology to verify their CPU cores by running them in a step and compare mode as part of their design verification. I'll come back to this a little bit later on, but this is a very powerful method of configuring our envelope model and being able to use it as a reference in your RTL environment for ensuring that registers have always got the correct values in them on a cycle-by-cycle basis. And I mentioned the difference between compliance and design verification. So we're part of the compliance working group, and our model is used as the reference within the compliance framework. What this allows you to do is to be able to build tests and then execute the tests on that reference model, and be able to generate the signatures which are used as part of that compliance framework. And in fact, we also a part of the bit manipulation group as well, and we're able to execute those those extensions in their current intermediate form. And as I mentioned, compliance is not verification, right? So the purpose of compliance is really to ensure that you've read and understood the specification. It's not about exercising the microarchitecture. It's about ensuring that what's written in the specification matches what the design intent is. Whereas with the microarchitecture, there are much more detailed tests that have to be written to be able to test things like in order, out of order, or hazard conditions, things like that. It's a different mindset to write your verification tests for the microarchitecture. And in fact, when it comes to testing, we should be very specific about this. That if you were to compare this to something like the ARM processor IP, currently within the test suites given for ARM processors, you're looking at something like 10 to the 15 verification cycles per processor. And so this is a huge amount of work that has to be done in terms of doing this kind of verification. And especially for when you get to the point where you're also generating your custom instructions, and you also need a model which will give you something that you can write your extensive tests on. And so when you take the OVP RISC-V models and embed them within a full Imperas simulation environment, then this gives you far more capabilities than you would have, for example, with the versions that are purely used for compliance. When it gets to design verification, you have to consider things such as having multiple hearts, the custom instructions, and also being able to be reactive to external asynchronous events. And this is really one of the things that we've concentrated on recently by providing these capabilities and giving a step and compare design verification flow as part of something like a system Verilog simulation environment. And there's already been some public announcements on this from one of the companies I mentioned there, Mellanox. Open Hardware Verification Group are using our technology as part of their fabric as well, their framework, sorry. And if you look at how this works, you basically have the base OVP model within a system Verilog wrapper using the DPI in order to communicate. And in that wrapper, what you will do is you will provide the access onto the bus to perform transactions for loads, stores, and fetches. And what you also do is you will expose out to the system Verilog environment the ability to introspect into our core model and be able to extract the values within registers, the current operating modes, anything that we have in terms of state inside the model. We have a programming interface that allows you to get access to all of that data and be able to use it in terms of comparing against your particular target that you're implementing. And the real benefit of this is that you can run this in a step and compare environment. And we have customers who are now doing this, and this is what we do as part of the Open Hardware group, where you have effectively two processors side by side, one which is the RTL implementation of the intent, and then an OVP model which is wrapped in DPI with the correct configuration parameters based upon the target that you're implementing. So you have to consider things like, does your design handle misaligned load stores? Does it handle compressed instructions, so misaligned addresses for fetches, this kind of thing. So you have to be aware of all these when configuring the device as your reference. And so just in summary, some of the things I think to take away from this is that our simulation is incredibly fast. We run billions of instructions per second inside our environment. We have some great analysis tools and debug tools that allow you to get in and extract lots of information from the execution of applications on the processor models, but also from a system perspective where you have your heterogeneous platforms. We have great detail in there for the performance and the profiling and the debug. And also, as far as RISC-V is concerned, we have a base envelope model that covers everything within the specification of the non-privileged and the privileged ISA, which means you've got a starting block for all the capabilities that are there. but you can then fully extend that with any custom logic that you intend to put within your part of your special design, such as your custom instructions. So I hope you've enjoyed this presentation. Thanks for listening.